about, okay, well, what is Km, what is Vmax, and all of that. So hopefully we can understand what Vmax is. Okay. And the impression that I had, even with you, Jimmy, is you're okay with Vmax. Everybody should be okay with Vmax. That is our maximum velocity for our particular enzyme. But this Km idea is this weird concept. What is Km? And I kept referring to it, and I'll still kind of maintain this, that Km is our binding, or a way to represent our binding affinity for the enzyme with the substrate, or between those two. And I always get this backwards, so you might have to check me on this. The larger the Km, the smaller the binding affinity.
It goes backwards.
Okay. So what does that mean, per se? Okay, well, that definition is really just to get us an idea of the attraction between those two. That's something kind of tangible. It really isn't something tangible because it doesn't directly represent that. It sort of does, but not really. Okay? If we look at our curve, all we've got is Vmax. So what if I had a different enzyme reaction that did this? Well, Vmax comes out the same, right? I'm attempting to have it come out the same. Would I expect the same enzyme activity?
No.
Why not?
It's inhibited. It's a different curve.
Rates are
It's a different curve. The curve at the beginning is different. That's it. Okay? If we just look at Vmax, both of these maxed out at the same level, but the enzymes are still functioning differently. Okay? So we need something else to describe the difference or the relationship between these two. Vmax doesn't do it all. What is Km really giving you information about? It's giving you information about the slope of the line at the beginning. Okay? When I'm in that first order relationship between my substrate and the rate of the reaction. Okay? It's again not a slope because it's really only giving us a single data point at the beginning. But if we know where Vmax is, we can kind of connect the dots out. Okay? So Km is officially the concentration of the substrate when we are at half maximum velocity. Okay? That is what it is defined as. Okay? Well, what does that mean? Well, really that just gives us an idea of the slope of the line at the very beginning of the reaction. Does our enzyme grab substrate and immediately max out velocity, or does it take a while to kind of ramp up? Okay. Does that make it any clearer of a concept of what Km is? Well, that's kind of for you. I would argue no. I don't think that makes it any clearer. But I'm kind of, in general, confused by that whole section. Okay. The next question would then become, well, why do we care? Why do we need this information? Well, that comes in when we move out of our standard normal enzyme function of substrate and enzyme to bringing in inhibitors. Okay. Well, if we now bring in inhibitors, how does that change our curve? How does that change the reaction? So if we looked at our standard plot, which I don't have actually here, I'll erase some space here. If we look at our standard plot for our enzyme activity, we've got our rate and our substrate concentration. Our normal curve, say, gives us something like that. Well, what happens if we get something like this? Well, Vmax didn't change, but the slope of our line changed. Okay? And let's say it was the same enzyme. Okay? We just pulled the enzyme out. One time we tested it, we got the black curve. Another time we pulled it out, and we somehow got the red curve. Well, what the hell happened? Okay? Well, we could go through and analyze what we pulled out of the cell and determine that the second time we happen to get some inhibitors in it. Something else is affecting that reaction. Now that we know something is affecting it, how does it affect it? What is it doing to the reaction? Is it changing Km? Is it changing Vmax? Is that important to know for that enzyme? Well, let's say the enzyme is the happy enzyme. Okay? It goes through and makes happiness. You got a massively depressed person. One of their potential conditions or symptoms, not symptoms, causes, could be that their happy enzyme stopped making happiness. Why did it stop making happiness? There's an inhibitor. Okay? So what could we try to do to help that person? Design something to get rid of the inhibitor. Okay? Or maybe we just give them a crap ton of drugs of the substrate result that's happiness. Just pump them full of morphine. Okay? Now they're happy all the time. Okay? So we're bypassing that entire system. Maybe it's the sadness enzyme. Okay? The thank you enzyme. It's the Canadian enzyme. That's why they always say sorry all the time. Okay? Because they've got this enzyme that's functioning overactive to make them say sorry every freaking day. We're like, God, it's annoying. Stop saying sorry. So we give them a drug that can then inhibit the enzyme and prevent them from saying sorry. Okay? We have to know how the enzyme works and what those inhibitors are doing in that process. Because if it's, say, a competitive inhibitor, okay, well, Canadians still say sorry. Well, what happened? The competitive inhibitor doesn't affect Vmax. Okay? It only affects our Km. So we have to give them a ton of the inhibitor. They have to ingest a ton of our anti-sorry drug to get them to stop saying sorry. So having an idea of how the inhibitor works can then say, well, how much drug do they need to take in? As opposed to how I initially talked about it, which was, what if I want to make the enzyme do something for me? Does that make a little bit more sense? So if we tie it back to drugs, it's what's the dosage that we need to be using? Okay, well, it depends how the inhibitor works. What's that drug doing? Okay. If it's a competitive inhibitor, we're probably going to need a ton of the drug because we have to overwhelm the substrate. Okay. If it's one of our other inhibitors, non-competitive or uncompetitive, we have to know how those affect Vmax and Km so that we can then again decide what dosage makes more sense. Kind of make a little more sense now? Does that apply to your broader senses?
Yeah, sure.
Okay. That's a big vote of confidence. Yeah, sure. Okay. But it's at least setting you up with the idea behind this. Okay. After that, this is ultimately what you're responsible for. This is your big summary of everything that happens. Your competitive inhibitors, Vmax will be unchanged. Why? Well, Vmax is when we have tons of substrate. If you have tons of substrate, they're both fighting for the same active site. If you have tons of substrate, you're overwhelming the inhibitor, which means Vmax doesn't change. You have so much substrate that there's effectively no inhibitor. Okay, so Vmax shouldn't change. But what should happen to the Km? Okay, well, the Km is going to have to adjust. If we look at the curve that I had drawn up there on that previous slide, there's our sort of standard enzyme kinetics. We said our Vmax doesn't change. It's going to have to somehow change the reaction. Well, what happened in this case? 1/2 of Vmax. In our standard reaction, there's our Km. With our inhibitor, what happened to the Km?
Bigger.
It got bigger. How did the inhibitor affect? It changed the slope in our first order reaction dynamics. Okay. Our Vmax stays the same. So it's a question of interpreting the curve and saying, how do these things then adjust the results we would see? Okay. And yes, we're doing it backwards, because the way it was initially done was experiment. Went in an experiment and saw that these things started to tweak off. How does that then relate back to our Km and Vmax? Okay. We can do the same kind of idea with our non-competitive and our uncompetitive. Okay. They get dicier to manipulate. Okay. But we can come up with ideas on how they're being affected. Okay. So if we look at our competitive inhibition, with all of these, what we're trying to do is get some sense of what's happening within our reaction. So we have our standard conditions on the right there. Enzyme plus substrate forms the enzyme substrate, goes to product. Okay. We also, under the competitive inhibition, the inhibitor can bind directly to the enzyme to form the enzyme inhibitor complex. That complex can't go on to form product. Because it's a competitive inhibitor, it cannot bind to the enzyme substrate complex because
It's already binded.
they're fighting for the same site. competitive. The active site is occupied in the enzyme substrate complex, or it's occupied in the enzyme inhibitor complex. Okay, so our inhibitor is only affecting the enzyme, the free enzyme. Yes.
So is the inhibitor gonna stay attached to that enzyme, or could it, at some point, it's gonna let go, at which point then?
Yep, it can let go. Okay, and that's what's happening with our equilibrium arrows there. Okay, and this is where we can kind of bring in our idea of our Km and our the next thing here. We bring in the concept of Ki. Well, Km was kind of our binding affinity for the substrate. What's Ki?
Binding affinity for the inhibitor.
Binding affinity for the inhibitor. So what we're kind of looking at is a relationship for Ki in that equilibrium, and sort of a relationship for Km, that's a capital M, in that system. Okay, I'm going to put quotes on that because it's not officially where you solve for Km. And by looking at the balance between those two values, we can then start to predict how these things would calculate out. Okay? And this is a massive algebra problem that I can go through and solve. I'm actually really proud of this. I was able to solve just using this information, in fact, just this information up here, and knowing what our first order rate kinetics are, the rate when we have low substrate concentrations, and Vmax. With that information, you can go through and substitute, and you can end up determining this big old nasty equation. Okay, this big old nasty equation should look kind of gross, but what happens if I simplify this a little bit and just erase this term? What does that equation become? Yes, there's a name for it. Yeah, we saw it, and it's last Tuesday because we had Thursday in the library. This is our equation of a straight line. So we had Michaelis-Menten kinetics. Okay. This is the equation for the Lineweaver-Burke plot. Okay. What happens under normal enzyme kinetics is that we would then say our y-intercept was 1 over Vmax. Once we know 1 over Vmax, we can then solve for Km off of our Lineweaver-Burke plot. If we move to competitive inhibition, what happens? We have to introduce this new term. What is that new term coming from? It's coming from, where did it go? Sorry, the Ki side of the equation. Because what's happening? Our total enzyme is now not dependent on just how much is in the enzyme substrate. It's also dependent on how much is in the enzyme inhibitor complex. Using that information, you can do all sorts of nasty, ugly algebra. That is, we have mirrors up in my house, and I've filled the mirrors with freaking equations. Okay? And you can get this equation down here. So looking at this equation, this is now our competitive inhibitor. Does Vmax change? No. If we look where we solve for Vmax, it's our y-intercept. Is there any new term to Vmax? No, absolutely none. Does our Km change? Well, where do we solve for Km? We need to know Vmax. Well, Vmax didn't change, so it's there. Okay. Km is changing by this extra factor. 1 plus the concentration of inhibitor over the binding affinity for the inhibitor. That value will be what?
Positive.
Positive. Okay. You can give me more information. What is the size of inhibitor over Ki? That will always be what?
Positive.
Positive, right? Your concentration of I and your inhibitor, or your equilibrium constant, need to always be positive. Well, if that's always positive, what is the size of that term in parentheses?
More than 1.
Always more than 1, which means the new apparent Km
Go up.
has to go up. Okay? And again, this is our apparent Km. This is what we're visualizing within the reaction because we can't separate those out cleanly. Okay? So we can actually prove those two systems, or really our Km system. Our Vmax remaining unchanged is us looking at the data and saying, well, what happens? Okay, Vmax is when I have a crap ton of substrate. If I have a ton of substrate and the inhibitor is binding for the exact same site, the substrate wins. Okay? So Vmax will remain unchanged. Okay? So Vmax, we just predict from the system. Km is something that we'd kind of have to go through and solve, because Km is dependent on Vmax. Okay? If you are interested in seeing that calculation all the way through, talk to me after class, or see me in the tutoring center, and I'll go through and solve it, put it up on the boards in the tutoring center. Okay? I will freely admit that in my solving of it, because it's all algebra, I definitely have not done it the short way. Okay? Maybe if I do it in the tutoring center, I'll luck into doing it the short way. So what happens to our plots? So our reaction velocity versus our substrate concentration. Okay, well, Vmax is unchanged, so if I'm going to draw a new curve on here, where's my Vmax? Well, same place. What happened to my Km? It needs to increase. Where is Km currently on that curve?
Let's say 2.
So if we go here, 1/2 Vmax, there's our current Km for our red curve. With the inhibitor, Km needs to increase, which means Km needs to be somewhere over here. So let's push it to the extreme. That needs to be our 1/2 value. And we end up with something looking like that. Ish. Make sense? Okay.
So when you do the 1 over those values, though, it actually looks like it gets like a steeper slope, right?
So when we do 1 over those values, so the blue line here is no inhibition. That's our standard Lineweaver-Burke plot. Okay? Vmax is unchanged. Where's Vmax in our Lineweaver-Burke plot?
Y-intercept.
It's at our y-intercept, which means when we add the inhibitor under competitive inhibition rules,
Should stay the same.
that point must stay the same for all curves. What happens to Km? Km increases. Okay, well, one of the things that we talked about was solving for Km by looking at the slope of the line, all that fun, nasty stuff. There's another way to do it. We can solve, instead of for the y-intercept, the x-intercept. And when you solve your Lineweaver-Burke plot for the x-intercept, you find it is negative 1 over the Km. Okay? So if Km increases when we add inhibitor, what's 1 over Km going to do?
Decrease.
It's going to get smaller. So what happens when we now add inhibitor? Our green line has to intersect at our Vmax line, so there's a point. And we know our Km increased, so negative 1 over the Km must decrease. I can plot 2 points on this curve. Because I know it's a straight line, all I need is to draw a line through those 2 points. What happens if I add even more inhibitor? Well, is that going to still affect the rate and all, or the Km again? Yeah, because in our equation, you increase the concentration of inhibitor, you're going to still end up changing your Km. By what? Increasing it or decreasing it? Increasing. Because the larger an inhibitor becomes, the larger this one value becomes, our Km becomes even bigger when we add even more inhibitor. What happens to Vmax? It stays the same. So if Km gets even bigger, what happens when I take negative 1 over the Km? It gets smaller still. So here's my 2 data points. What do? Because I know it's a Lineweaver-Burke in a straight line, all I got to do is draw my line through. There's the line. So by running a series of experiments, we can look at our results and say, that matches competitive inhibition. So I could just give you this plot, the Lineweaver-Burke plot, with those inhibitor curves on it and say, okay, what type of inhibitor was it? Well, you have to be able to look at it and say, what happened to Vmax? Doesn't change. What happened to Km? Km was changed by increasing. Why is this weird? It's backwards because it's 1 over. Okay? So if you have this kinetic effect, what I've been putting in bold in virtually every slide that looks at these, you're then just matching it up to the data that's off of our curve. Kind of make sense?
Is that what you're gonna do on our test? You're gonna give us a graph and say, okay, is this competitive, is this
That
non-competitive?
is a perfectly valid question to ask.
Okay.
Yep. What happens in non-competitive inhibition? Well, this again comes back to what are we referencing when we look at non-competitive inhibition. And again, more than likely what happened is someone looked at the Lineweaver-Burke plots when an inhibitor was present and said, whoops, that does not match. First off, just normal kinetics. Something's changed with this other molecule present. Okay? Not only did something change, but it doesn't match the curve that I would have expected for competitive inhibition. So this must be a new type of inhibition. Okay? Well, this new type can't be competitive, so I'm going to call it non-competitive. Okay? So how does that change? So we end up back calculating our end results. And this comes back from understanding, or now once we back calculate what happened, we can define what non-competitive inhibition is. In this case, your inhibitor is binding to an active site at any time during the reaction. Or sorry, a site other than our active site at any time during the reaction. Okay? So if we look at our reaction, our free enzyme can interact with the inhibitor to form our enzyme inhibitor complex. Our substrate can bind to the enzyme. The inhibitor can bind to the enzyme substrate complex, and the substrate can bind to the enzyme inhibitor complex. As long as I'm in the inhibitor bound state, I cannot make product. Okay? You'll notice we've got all these extra terms floating up here. And you'll notice that when we look enzyme to enzyme substrate and enzyme inhibitor to enzyme substrate inhibitor, we're showing the same values. Why are we showing the same values? Why is this not S prime minus S prime?
What does prime mean?
Prime is meaning a different substrate binding affinity or different rate constant for that substrate.
Because it doesn't, it's non-allosteric.
It's non-allosteric. The binding of the inhibitor does not affect the substrate binding. That's it. Okay. What if it was allosteric? That's chapter 7. We'll see that today too. Okay. So in this case, the affinity for the substrate for our enzyme, okay, does not change. I wonder if we had a term that represented the binding affinity for our substrate and our enzyme. What was that term? The Km. Okay. The inhibitor does not affect the Km because the substrate can bind to any point within the curve. So Km remains unchanged during the reaction. Okay, so this is an interesting one. We actually came up with Km first instead of Vmax. Okay. What about Vmax? What should happen to the maximal rate?
All stuck up in
If we put inhibitor in there, can I make product? No. Okay. What if I put in tons of substrate? The inhibitor is still going to bind the enzyme and prevent that enzyme from functioning. Vmax will necessarily have to decrease.
How does it prevent it from functioning if it's not changing the structure?
So how does it prevent it from functioning? So where on this curve is it defined as functioning for an enzyme on this little plot? When you say an enzyme functions, what are you looking at? Say, oh, it worked.
You create product.
You create product. Where do we create product on this diagram?
Yes,
When the ES breaks into the E.
Right here.
and that's it.
And that is it. Okay. Why would Vmax be changed? This is the only place I can form product. When the inhibitor binds to the enzyme, can I go from enzyme inhibitor to product? What happened to the effective concentration of the enzyme?
Went down.
It went down, which then means that the rate is going to be, just a sec, down. Okay? Because I have less enzyme present, the rate will necessarily drop. Yes, can you go from the enzyme inhibitor to the enzyme inhibitor substrate? Yes. Can you make product from that? No. So our total, we can still go up, but if we look at our total enzyme, let's say we have 5 enzyme molecules, that's going to determine our maximal rate, how much enzyme is present. What happens when the inhibitor binds?
We only have 4.
You only have 4. Okay. Yes, that inhibitor can then go through the enzyme substrate inhibitor complex. Can it form product there? infinite form product?
No, it has to go back to.
No, it has to go back up to there. Okay? So during that time, when it's transitioning between all those phases, what else can happen? An inhibitor can bind different enzyme.
Yeah.
Okay? So the presence of the inhibitor is going to remove enzyme from the system. Okay? And that is going to be dependent on the relationship between the enzyme and the inhibitor. How much is present? How tightly does the inhibitor bind the enzyme? Okay? If the inhibitor, if those interactions right there are relatively small, what does that mean?
It's not going to have that much effect.
It's not going to have a huge effect on the reaction because the enzyme or the inhibitor is not binding to the enzyme very tightly. Okay?
Very minimal.
So we see a very minimal change in our observed Vmax and our Kms. Okay, but there's still an effect. Okay, so again, we go back to our curves. Okay, our Vmax for our red curve, there's our half Vmax. So there's our Km for no inhibition. What happens with our new curve? What happened to Vmax?
Goes down.
It decreases. So let's draw Vmax lower. Okay? Anywhere lower. Does not matter where. Okay, but Vmax should decrease from the uninhibited enzyme. Km, what happened?
Stays the same.
Stays the same. How do we solve for Km?
Half of Vmax.
1/2 Vmax. Vmax has changed, so I have to have a new 1/2 Vmax. That new 1/2 Vmax, roughly here, right? Okay. And we're saying Km remains unchanged. So we determined Km by going 1/2 of our Vmax before. That means our new data point needs to be here. Because the Km value did not change. I drew that kind of ugly, but you get the idea.
And that's because the affinity for the substrate of the enzyme isn't changed, that's still what it was.
Yep. Because the substrate can bind to the enzyme at any point during the reaction. So the inhibitor does not affect the substrate binding. Well, if it doesn't affect it, the binding affinity can't be changed either. Okay. So there's our standard curve. What happens when we move over to our Lineweaver-Burke plot? We'll again apply this information. Vmax decreases. Where do we determine Vmax on our Lineweaver-Burke? It's our y-intercept, and officially it's 1 over Vmax on our Lineweaver-Burke. I'm just going to say LB. So if our Vmax decreases, what happens to 1 over Vmax? It increases. Smaller Vmax, 1 divided by a smaller number is a bigger number. So we go back up to our curve. When we add inhibitor, what happens?
It increases.
Oh, those stupid labels. So let's go through and clean that up a little bit. Let's say this one is no inhibitor,
You had a -1.
I believe. And I think that's what they're trying to say with a -1. Okay, what happens to your Vmax? Vmax decreased, so 1 over Vmax must increase, which means on our curve, our new line, we know we have a data point up there. Okay? What happened to Km?
Stays the same.
Stayed the same, which means the x-intercept needs to be the same place. Because it's Lineweaver-Burke and I know I've got a straight line, there's my curve. Okay? So it's being able to look at any one of these plots and saying, okay, how do I know what type of inhibition is happening? You're going at it backwards because you're looking at the end result that someone came out of their experiment, back calculated and said, these are the things that changed. You're now being told you have to know what changes. What does that mean the inhibitor is? Okay? Does that suck for you? I would argue not. That's actually probably a lot nicer than looking at all the data and trying to back calculate. Okay? Questions about the non-competitive? One of the things you'll notice is that if you look at the curve, they've introduced this 1 plus 1 over Ki. We saw that before. That came out of all the way back here. You notice it showed up in here. Okay. That comes from, that equation or that piece comes from looking at how the inhibitor affects the enzyme. Turns out that that piece is consistent across all the different mechanisms. Okay. It's just a question of where that piece shows up, or if it shows up multiple times.
So the non-competitive will be now next to the KM.
It's going to be part of your KM, so that when we look at where we, or sorry, Vmax. When we look at our Vmax curve, there it is. Our term is showing up. Should it show up with the Km? Well, the Km is supposed to be unchanged. It had better not show up with that one. Okay. If we took the equation of the line and broke this down, you would see the 1 plus I over Ki showing up in your slope. So well, isn't that affecting Km? No, because remember, that term is already affecting Vmax. It has to show up in both locations in your Lineweaver-Burke. Okay.
Go back one slide.
Just that slide?
Yeah, I just want to see where what it looks like, how the equation changes.
So I don't have the full Lineweaver-Burke plot. I can draw that out here. Because we are plotting, what is it, 1 over Vmax? No. 1 over V. 1 over our rate will equal Km over Vmax times 1 plus our inhibitor over Ki. And then is it minus? No, it's got to be plus. 1 over Vmax times 1 plus I over Ki.
Would you have it in both places? Because wouldn't that then change your KM? Do you have it on the left side too?
But remember what happened to your Vmax. Your Vmax is being altered by this, so that factors in here.
Oh, it does.
Yeah. So when you solve, it'll end up canceling out. And I left off the substrate. Your substrate's in here. Because your Vmax is now altered by this amount, which then means when you alter it here, those terms would cancel. See what I'm saying? Yep. This one I have yet to solve the algebra on. And I'm missing some assumption. There has to be a simplification that I'm just missing. What happens in uncompetitive inhibition? Again, more than likely, oh shoot, this one doesn't have a nice curve on it, so we'll have to draw it on. What would happen is we'd go through and look at the Lineweaver-Burke and our standard enzyme kinetics and say, whoop, something weird's going on here. What happened? Okay, well, it doesn't match the competitive inhibition curve. It doesn't match the non-competitive inhibition. Okay, well, it makes sense to have competitive and non-competitive. Well, what the hell? If it's not competitive and it's not non-competitive, what do we have? Well, then it's not competitive and it's not competitive. So we end up with a new term, uncompetitive. We can't call it competitive, and we can't call it not competitive because we already had that one. So they end up adding a new type of inhibition. This is our uncompetitive inhibition. Okay, well, what's happening here? Based on looking at that data, they back calculated and said, okay, this is what changes occurred. That must mean that in the uncompetitive inhibition, your inhibitor binds to the enzyme substrate complex, but only to the enzyme substrate complex. So when we look at our reaction, it kind of simplifies down. The inhibitor can only interact with our enzyme substrate. Okay, and officially there's a minus I in there too. This is just copy, paste, and covering up stuff I didn't want. Okay. Well, how does that affect everything? Well, what's going to happen to Vmax? It's going to necessarily go down. Why?
Because K2 and K minus 1.
The only place where you can have the reaction occur is when you're at the enzyme substrate complex. But if the inhibitor binds to that complex, do we have that complex anymore?
Nope.
Nope. You can't make product, which means your maximal rate will go down. Vmax has to go down. What happens to Km? This one's weird. Okay? In the previous cases, we said Km was unaffected. Okay? And that's because the substrate could bind at any given point. what's happening here? We're removing the concentration of the enzyme substrate when the inhibitor binds, which means that disappears. What is that going to do to the balance of K1 and K minus 1?
It's going to change it.
It's going to change it. It's now going to try and shift the equilibrium to replace that. We're going to see an apparent increase in K1 because we're trying to replace that in our equilibrium because the inhibitor is removing it. Okay? What does that mean? Km will necessarily change. And it's going to change in a way to make more enzyme substrate, which means what's happening to the binding affinity? It's becoming more attractive. And remember the relationship between our binding affinity idea and Km? They're inversely related. We're seeing a stronger affinity for the substrate in our enzyme, which then means Km decreases. Because the equilibrium looks all simple here, theoretically I should be starting with this one, and I might be able to solve this one better than I could the non-competitive. Okay? But we'll end up going through and predicting similar kind of features. How does this change our curve? Both Vmax and Km decrease. So let's look at our new curve. Okay? So here's our old Vmax in red, our old Km in red. What happens on this new curve? Well, Vmax needs to decrease, which means we have a data point, again, arbitrarily lower. What about our Km? It needs to decrease. Okay? This becomes a little bit more challenging to deal with. Okay? So there's our Vmax line, so our half Vmax is here. Okay? And Km needs to be somewhere lower. Those two intersect somewhere about here. Again, horribly drawn, but you get the idea on it. We're going to end up with a steeper curve at the beginning. What did we say steeper curve meant? Okay. An increased affinity for the enzyme substrate complex, which is Km. Okay. So we can now kind of interpret based off of our rate versus our concentration of our substrate. Notice that all my curves look nasty and ugly because they're all kind of overlapping and intersecting in roughly the same area. It's all dancing around that Km value. That's not easy to interpret. So what do we end up doing? Lineweaver-Burke. And when we change our Lineweaver-Burke plot around, this is where our information helps. Vmax decreases. What happens if Vmax decreases? What happens to 1 over Vmax? 1 over Vmax increases. So I end up with a point further up my line. What happened to Km? If Km decreases, what happens to negative 1 over Km? It gets bigger. Good thing we've got lots of space out here. It gets bigger. And what do we end up noticing? Come on, pencil.
Wait,
Seriously?
Isn't it supposed to be the other way? Isn't it supposed to be
Km,
zero?
the 1 over Km gets bigger, but it's a negative value. So when we said increase and decrease, we didn't factor in the negative value.
So how
So-
come on your competitive inhibitor plot, when you had it getting closer to zero for the more
Because
inhibitor?
1 over Km, so again,
Oh, because it increased.
1 over Km increased.
All right, okay.
So we're moving to a less negative value. Yeah, negative signs are the bane of all science. Okay. The end result, okay, interestingly enough, is that we actually get lines running parallel to each other when we have the inhibitor. Because they're both being scaled by the same amount. Okay. So by looking at the curves, we can determine what type of inhibition we've got. Once we know the type of inhibition, we can then potentially design a drug to target those sites more effectively, or even the dosage. Okay? Questions? Okay. The last one's nasty, and the textbook doesn't really talk about it. They have one paragraph. This is lovely. You have mixed non-competitive inhibition. What's happening in a mixed non-competitive inhibition? Okay, your inhibitor is binding at a place other than the active site, hence the non-competitive. Okay, but maybe it prevents the substrate from binding. Okay, What does that do with your curve? That
It's all over the place.
makes it a mess. Okay? And it's one that I don't have memorized, hence if we pull down the slide a little bit, intersects in the left side, what we're referencing there is something along these lines. Okay. What happened to V max? V max decreased because it went to a larger 1 over V max. What happened to Km? Our Km increased, yes. Okay. Which doesn't match any of the previous results. Okay. This kind of system is ultimately happening when we're looking at the relationship between your Michaelis-Menten, your binding affinity for the substrate, versus Ki, the binding affinity for the inhibitor. Okay. Depending on the magnitude of those binding affinities, their relationship to each other messes with the type of competitive or non-competitive inhibition you've got. Okay. Questions? Deep breath, the big ones you were tested on, because I don't think I've got the summary there. Right here. Those three, I want you to know those three. The mixed non-competitive pops up because it shows up in sapling. Shows up in your online homework. So if you can't get one of these to match the homework, then you know it's your mixed non-competitive. Okay? I know, that's super satisfying, right?
Example of a mixed non-competitive in the real world, or is that just like a?
I don't have an example for any of these, actually. Okay, so now we'll move into chapter 27, okay, which only throws in another wrinkle on this. So chapter 27, for some reason, they've kind of split things a bit oddly here. Sorry, 7. The beginning of chapter 7, they start talking about some experimental cases with, what is it, AT case? ATC ACE, I think. I think I removed the information from my slides. Where they gave a real-world example, and they said, well, what happens to the enzyme when this is present? Well, what happens to the enzyme when this is present? Okay. It's not, I don't think it's ATP. And it's interesting, because what ends up happening is they end up not matching any of the curves we just talked about. So what does that mean? Something else is going on. What's that something else? Okay. So as a big hint, what they noticed is that when they looked at the substrate versus rate curve, our standard enzyme kinetics that we just talked about should have something along those lines. What they got was something like this. So the black one was our standard, okay, typically referred to as our Michaelis-Menten kinetics. The red one is our, you guys have already seen this, our sigmoidal shape, which referenced allosteric control. And remember when we talked about allosterics, it could be an inhibitor and it could be an activator, so it can change how the reaction works. Okay? So they talk about the general case with our AT case, or ATC ACE, and then they go through and look at kind of the breakdown like we just went through and did with our enzyme substrates and inhibitors, and how does that change how we look and define Km and Vmax. Right out of the gate, we should have a problem. Km is defined as the infinity for the substrate and the enzyme when? During Michaelis-Menten kinetics. Can I have a Km for allosteric control? No. Okay. Can I still have a concentration of substrate that solves for half Vmax? Yeah. The concentration of substrate at half Vmax. So Vmax is there. I can determine this concentration of the substrate at that value. Is that the Michaelis-Menten Km? No, because it's not following Michaelis-Menten kinetics. Does it still give me some information that's similar to the concept? Yes, but I can't call it Km anymore. I have to call it something else. What do we end up calling it? You read ahead in the textbook? K a half. K 0.5. Okay, that's it. So mathematically solved the exact same way, but it loses a lot of the meaning. Okay? Some big keywords that pop up: allosteric, feedback, your pathways, homo and heterotropic, kinases, proteases, and coenzymes. Make sure you know those definitions. We'll look at some actual enzyme modeling, which is kind of fun, or not so fun because I actually read the second part of that, are active versus inactive. Interesting effectors. So we'll look at some cases of phosphorylation and zymogens, what they're referencing, and then the organics of an actual enzyme reaction. So there's my happy spot. Okay, everything else, yeah, but my happy spot in the organics part. Okay, where we're looking at what types of reactions are occurring within the active site. Okay, so feedback inhibition. What do you think it means? It inhibits.
It goes forward, whatever comes out, inhibits the process of.
So let's say D inhibits enzyme 1. So what happens as the concentration of D goes up?
The rate goes down.
Right? The rate of enzyme 1 goes down, which then means what happens to the concentration of B?
Goes down.
C.
Down.
D, well, that's kind of weird. What should happen to D? It's no longer being made, so we're now competing against it being destroyed somewhere else. Okay, so feedback inhibition is just saying the product of your reaction acts as an inhibitor in said reaction, somewhere in the chain of that said reaction. That's it. Yeah. Okay, so enzymes with allosterism, this is fun. So remember allosterics was referencing changing of shape. Okay, so sterics from organic was all about shape, where the electron clouds are. Allo is referencing change. So if we change our shape, how does that affect our reaction? Okay. Our effectors can either be a positive or a negative effect. If they're positive, we refer to them as activators. Okay. If they're a negative effect, we refer to them as inhibitors. Okay. Our substrate could act in either case. Well, actually, it can't act as an inhibitor because the whole point of the substrate is to make a product. Okay. So our substrate could act as an activator within the reaction, like, say, oxygen with hemoglobin. We bind oxygen, what happens? It starts to bind more oxygen. Okay? So it is a positive effect. It's an activator. So our substrate acts as an activator in that case. Doesn't always, but it can. Okay? Our negative effect, something binds and prevents the binding of our substrate. That's going to be our inhibitor. Our product, in a feedback inhibition, could act as an inhibitor. Okay? So what ends up happening in these cases? So if we go through and take a look, we get a couple different cases. So we got our reaction velocity versus our substrate. You'll notice all of these curves are sigmoidal. Okay, so our blue thing is without these activators or inhibitors. Okay, that's our standard curve, and we see that kind of sigmoidal shape. What happens when I add ATP? The velocity at the beginning goes up, meaning it's activating. We're getting more product because the rate's getting faster. That was kind of fun to say. Okay. What happens in the case of CTP? We add CTP, now what happens? Okay. The rate of our reaction slows down, which means CTP must be acting as an inhibitor. That's it. Okay. So you're just looking to see how the curve changes from your standard state. That's the kind of be-all, end-all of what you want there. Okay. There are a couple things that we should be looking at, our Vmax and our Km. Okay. If we change Vmax, does that necessarily change Km? No. If we change Km, does that necessarily change Vmax? No. Okay. So this brings up our new issue. Vmax, that's going to be consistent across all mechanisms. This is the fastest our reaction can run. But Km no longer applies here. This is where we first introduced the idea of K 0.5, okay, which is more realistic from how we determined it. Because how did we determine Km?
Half of the Vmax.
It's half Vmax. It's the substrate concentration at half or 0.5 Vmax. So it's still the same kind of concept. We just can't call it Km because it's not that kinetics. Okay? So when we look at our enzymes, the enzymes can get subclassified into two different categories. Either a V system or a K system. What do you think a V system means?
Affects the Vmax.
Are inhibitor or activators affecting Vmax? A K system?
That's the K.
It's affecting our K.5. Okay, that's all we're trying to get out of it. Okay. Why K.5? This curve or this data came from our Michaelis-Menten, which is why we had K.5 or Km. Okay, that's why we ended up using Km. We have a sigmoidal curve. As soon as it's sigmoidal, this makes no sense. Because in a sigmoidal system, how many different relationships do we have? We have a first order relationship down here, we have a first order relationship here, and a zero order up at the top. There's 3 different rates for an individual reaction, depending at where you are with your substrate concentration. Okay. In a standard enzyme reaction, and we can kind of look at the red one, standard enzyme we have first order and we have zero order. That's how we solved for this expression from our Km, or to get our Km and Vmax relationships. We had 2 rates within our equation. The sigmoidal curve has 3 rates, so officially we can't make that connection. Okay. Interesting though, what happens to our curve as we add activator?
Looks like it becomes more like a 2-rate one.
It starts to become more like our standard Michaelis-Menten kinetics. Right? And we lose some of that sigmoidal or allosteric effect. Because now it's saying, well, now I just want enzyme, or I want substrate, just give it to me. That's what our activator is doing. Okay. What happens as we add more inhibitor? We're increasing that sigmoidal effect and potentially dropping our Vmax. Okay? So, within this, we've got a couple things to look out for. So we get 2 primary mechanisms known as the concerted and the sequential. Both of them center on this center topic at the very bottom here. Okay? So we are looking at a 2-part enzyme. Okay? In one part, we'll reference as the R, and the other part we'll reference as the T. Why? I don't know. Okay? Which makes even more sense when we reference what R and T represent. R represents the form of the enzyme that I'm calling substratable, meaning it can bind the substrate. It has a higher affinity for the substrate. T happens to be the form that is unsubstratable, meaning it has a lower affinity for the substrate. So our enzyme is now stuck or kind of oscillating between these 2 states. Okay. The more R state we have, the more likely it binds substrate. The more T state, the less likely it binds substrate. Okay. The names for those, again, no idea why. The R they reference as the relaxed. The T they'll reference as the tight or taut. Don't look at me. Okay.
You know, right, that the enzyme changes between both of those.
And the enzyme is changing, exactly right. So within this image, because I cut it out, you can't see it, but the substrate is supposed to be like this little rectangle thing. So it can fit into the R form. If we look at where it would bind in the top form, it doesn't have that perfect shape. Okay, so the substrate would not likely bind in that state.
That's due to an inhibitor? Or just the
That's
enzyme
due to
itself?
the enzyme shape itself. Okay? And it has to have a varying state or a varying interaction. That was not enough. We also now introduce the balance between those 2. And the balance between those 2 now needs to be a ratio. Okay? And that ratio will pick to be defined as L, God knows why. And it is defined as the taut form over the relaxed form. Okay? So what does a large L value mean? Mostly in the T form, which means low substrate affinity, unsubstratable. Okay. What happens if we have a very small T, or a very small L? Then our enzyme is reacting very quickly with our substrate. Okay. So what would we predict to happen to the curve? Okay. So we have our standard sigmoidal curve. If we call this our red curve and our blue curve, what would we expect our red curve to look like? More like Michaelis-Menten. The substrate wants to bind. We have a very high affinity there. So we would expect more of a Michaelis-Menten system. Okay. If we're more in the T curve, less likely to bind, we're going to get more of that kind of sigmoidal drop-off. Okay? So we can use that L value to predict something about kind of the angle of that first rate. Okay, so now what happens when we're looking at our concerted mechanism? So our R form binds substrate tightly, okay? So our structure becomes changed to bind it better. Our T form is our native state. So this is interesting. Our enzyme starts in the taut form, the unsubstratable form. Okay? Because if it started in the R form, we wouldn't be looking at a sigmoidal curve, we'd be looking at Michaelis-Menten kinetics. Okay? So if we're looking at an allosteric enzyme, most of it starts in the taut form. It is going to favor the taut form. That's how we know it's sigmoidal. Okay? Because otherwise we'd be in the Michaelis-Menten dynamics the whole time. The substrate does want to interact. It has a higher affinity. Does that make sense? Okay. So our standard value for L should be relatively large, because our enzyme is going to start in that form. You give me a quizzical look, explain it.
Just trying to,
Process it all?
process that. The fact that, like, when we talk about the way we were just doing it had to do more with non-allosterics, and this is allosteric, so does
The R form, though,
make it non-allosteric?
Yep, because the R form has an increased affinity for the substrate than the T form. So if we started in the R form, what we've got is Michaelis-Menten kinetics. It already wants to bind the substrate. The T form doesn't want to bind it. So if I started largely R, it's Michaelis-Menten. It already wants to bind the substrate. It's starting in that condition. Okay? So if we're going to move to this allosteric control, we are primarily keeping our focus on the taut form. That's got to be our higher concentration, because now it doesn't want to bind. So if we looked at our curve, we'd see a very slow rate at first, because the substrate doesn't want to bind. Okay? As we increase the substrate, we increase the affinity. That's now going to be a dance between this taut and this relaxed form, deciding how does that translate.
So if it's non-allosteric, that's because it's already in a favorable conformation.
Exactly right. Exactly right. It's already in a favorable conformation.
So the pH or the heat of the environment the enzyme is in will help cause it to change.
So interesting. We haven't even addressed that. If we change the conditions, will that change the shape of our enzyme? Yes. Okay. Changing the shape of the enzyme is going to potentially change it outside of the bounds of relaxed and taut. We could very well be changing it to completely screwed, okay, and non-functional, which isn't really taut because it's now not even in a state where it could potentially change. It's screwed.
That doesn't relate to this.
That does not relate to this.
That atom and the electrons moving
This
around
is
make it
looking at,
change, and
yep.
then- okay.
We're looking at our enzyme in its native state, and as we mess with it by either adding substrate to get it to react, or adding inhibitor to prevent it from reacting, or adding an activator to make it react faster.
All right,
Okay.
so we're adding things to the enzyme.
We'll be tweaking this state by adding some other piece. Yes.
Not changing the environment, but adding substrate like blood.
Yep, exactly right.
Adding something else to change.
Exactly right. Right. So our L form we already talked about is the balance of our inactive and active. Okay. C, an extra fun thing here, is now the binding affinity. Okay, or the relationship of the binding affinity for the R form with the substrate and the T form for the substrate. Okay? So looking at that relationship between them, well, what does that mean? Okay? Kr, if we're saying the binding affinity, Kr is really big, what are we referencing there? Okay. So if C gets big, we're saying Kr is larger than Kt, which means the binding affinity, we have that stupid inverse relationship, I believe, on this. If we start at a very small C value, okay, meaning the binding affinity, yeah, it is inverse relationship. This goes back to the same thing we saw with our Michaelis-Menten. Okay, if we have a small c, that means Kt is larger than Kr. Okay, what does that mean the binding affinity is for Kt? Does it really like the substrate or really not? It doesn't like it. Remember that inverse relationship with our Ks and our binding affinities. Yeah, isn't that lovely? Okay, which means if we have a small c, should we be more or less sigmoidal? More sigmoidal. Small c, more sigmoidal. Okay? Because we're saying that Kt, we have a very weak attraction between our substrate and that form, which is important. Okay? The less attracted our top form is for the substrate, the less active the enzyme is, which means more sigmoidal. Okay? So we can now look at our C values and our L values to look at how those things change.
How come they do, on this particular thing they're doing, you got your T1 is on the bottom and your R is on the top, where we did look at the L thing, it was the opposite.
Yeah. I'm a biochemist. That's kind of my response. More than likely what they went through and did is looked at those relationships. I'm going to actually guess because of that inverse relationship between the size, the magnitude of K, and its meaning back to the binding affinity. Because of that inverse relationship, we have to exchange those locations. That's probably why, so that it makes more sense off the curve. So we can look at an L value and we can look at a C value and start to predict how is that going to change our relationship, either being more sigmoidal or less sigmoidal. Okay. Our L form, very, very large L value, meaning mostly in the top, we become exceptionally sigmoidal, which is exactly what we talked about before. Okay? The larger our L value means the more we have of our T, which means the more sigmoidal. The more of our inactive form we've got, the more sigmoidal we become. So both C and L are getting at the same concept, just from different angles. One's looking at kind of an equilibrium constant, if you will. The other one's looking at concentrations. Okay?
So C is concentration.
C, yeah, wouldn't that be lovely? C is the ratio of our binding constants. Yeah. So L is our concentrations. Which do we have larger of, T or R? C is our ratio of our binding constants. Okay. So we now have that ability to kind of look at those relationships, and yet we still haven't even talked about concerted or R sequential.
So could you have where you have kind of like opposite, where you have a lot of R, but your ratio, your constants, like.
That's an interesting idea. I'll look at that. Because, yeah, then you'd have counteracting things. You may, because if you had a lot of R, L gets really small, so you start to shift to being more Michaelis-Menten. But if your relationship of your binding constants went to being more Kt, that makes it more sigmoidal, and you could have a counteracting. Yeah, I don't know. Mathematically, yes. Okay, so breathe, take a minute to look at this. Okay. So what we're now looking at here is what happens in our concerted mechanism. Remember, our focus is with all the L and the T, or L and C, which is all sitting up at this top portion. We're looking at the balance between those two systems. and how these would affect our individual relationships. So, if we add an activator, what does the activator do? It will react with our R form to activate the enzyme so that it binds more substrate. What happens to the concentration of R?
Goes down.
It goes down. Because we're in an equilibrium, what does our equilibrium then do? Shift to make more R. What happens to the balance between T and R? T goes down and R goes up. The ratio between T and R starts to shift. What does that mean happens to our Allen C? That then starts to shift. If we end up shifting to making more R, we get a less sigmoidal curve. Okay? And we end up seeing our Michaelis-Menten kinetics. So as we add activator, the activator shifts us into our Michaelis-Menten system. What happens if we add an inhibitor? Well, the inhibitor binds to the top solution, or top form. What happens to the concentration of the top form then? If the inhibitor binds, do I have the top form anymore? No, I have top plus inhibitor. So what happens to the concentration of the top form?
Goes down.
It goes down. Equilibrium, what happens?
And R shifts to T.
R shifts to make more T. As I make more T, what happens? I go more sigmoidal. As I add more of my inhibitor, I shift to form more of a sigmoidal curve. Okay? So in this mechanism, we're still centered on just the balance between our active form and our inactive form. What does the inhibitor do, or what does the activator do to cause that equilibrium to get out of whack? As it gets knocked out of whack, that affects our relationship between C, or between R. Not R, what's that other one? L. Okay. We could also apply that back to C by looking at how tightly our activator or our inhibitor binds to each of those. Okay. If we put in the activator, what happens to the binding affinity for the substrate for the R form? It increases, which means, where's that stupid value? What did we say C was? KR over KT. If our binding affinity goes up, what happens to KR? Remember their inverse relationship. That should go down. And as it goes down, oh no, that puts us, it needs to be getting bigger. So what happened there? As we add activator, our affinity for the substrate increases. KR should get smaller. KT should change, should not be changed, so C should still decrease. Interesting.
Won't KR get smaller? Isn't it we're getting more?
Because
affinity?
they were inversely related, right? Your binding affinities? Yeah, I think that's true. So avoid C. Let's put it that way. I won't ask on C. We'll ask on L, because we're drifted to the end of class and I needed to get into the next chapter. So, and we're not even close. So we'll just not ask questions on C.
So just focus
Okay.
on L.
I won't ask questions on C as far as activators and inhibitors. I still have the question here. The lower the C,
The more sigmoidal.
the more sigmoidal. That is still fair game.
So we need to know that. Okay.
Okay. And by Thursday, I'll try and figure out what's happening with our activator binding and how that affects C. Okay. Okay. Yeah, I don't blame you. And that doesn't even bring in our sequential. So I'm going to real quickly, our sequential, our enzyme has two states. Okay, and this is our quick spinball. Our enzyme has two states. They both start in the top form. In active hand cramp. Our substrate binds, which then changes our top form into the relaxed form. Because our
taut form has now changed to the relaxed. What does that then do to the other taut form? It helps it relax to now increase the affinity for our substrate. Okay. So we've got our substrate binding in a positive cooperativity effect, or in the bottom one, a negative. Our inhibitor binds, that makes it even more difficult to get it shifted over into the relaxed form. Okay. So